Right, is this thing on? Yes it is. Let me just check it's coming through. Yes it is. Let me just check it's coming through. Awesome, okay, cool. Yeah, I didn't upload because I was moving into a house, or home. It's not a house, it's an apartment. And I had to wait for things and do lots of cleaning and stuff, and so finally back on it. I think today I'm going to just review what I was doing because it's kind of sketchy in my mind. I remember I was doing something about periodic table and electrons, protons, neutrons. So I need to remind myself of that, and I think I'll keep it there. Then I'm going to get some lunch, and I might stream a little bit more later. But then I've got to do some code for my other stuff. So that's what we're going to do. Alrighty. So as always, we're going to start with Greek. Here we go.
Z.
That was really quick. Let me just try that again.
Z.
Z. Okay.
Z.
Oh, also the mic, different headset because the other one's not quite working. That's the Razer. Razer something version 2. I don't know, whatever it's called. I had to send it back, so that's going to be a week or so. And then we'll get back to the slightly better quality. Select the correct characters for Zo.
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 Ze.
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 Match the pairs. Ze. Ze.
Ze.
Z.
Z.
Z. Zo. Zo.
Zo.
An. An.
Mi.
Me. Me.
Ze.
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 The pink carrot. I think it's rose. Rose.
Rose.
So it'd be to,
To.
rosa,
Caroto.
caroto. To, rose, caroto.
Z.
Z.
Z. Ne to rizi.
Ne,
Ne
to,
to
rizi. This is the rice. What is that? Can't remember what that means. Yes, okay, yes, the rice. Okie dokie. The pink water. Ah, damn it. I always forget to do this. Keyboard. I'll remember that next time. I probably won't. So it's to. Oh, actually need to type in there. To. Ro is the P, the O, and the Z. And then water is Cafe Nero, so it's Nero, N-E-R-O. Oh yeah, check that out. Oh, we've got some flicky things though, accents. Yes, the rice. So yes was nay? Nay? Can't remember. Oh, it was. Nice. That's good. To ris. I think it's that. Ooh, okay. Got the U in there. Risi. So it's nai to. Whoops, Risi. And it's got this accent as well. Let's try that. Oh, I don't know how to do them in this keyboard. Is it that? Maybe it's that. No. Yeah, I don't know how to do it. Nice. So let me go back to English. Alright, that's that done. So let's check over what we did in episode 6. I might have to go through episode 4. We went through the CRISPR documentation again. We're going to read through the episode 3, probably worth remembering stuff in episode 5. Interesting. What we did, periodic table. Yeah, we had a look at that. Discovered atomic numbering, protons, electrons, neutrons. Started to look at a tool that might be good to plot chemical structures. Looking at chemical formulas and structures. Oh yeah, the condensed form is the Lewis structure, the skeletal formula. Okay, yeah, this is all good. But I think I'm just gonna revise probably up to 12:15, something like that, UK time, GMT, and then I'll go grab some lunch and might come back. Depends on how I'm feeling. I'm very tired because I had to wake up very early for my washing machine to be fitted. 7 in the morning, ungodly hours. Revise this structural formula. Okay, and then what we want to do next, continue reading this wiki, structural formula, try and draw some of the components of the nucleic acid. Whoa, got a bit ahead of myself there, I guess. Oh, as well, I should probably have chat up as well, just in case. However I do that. How do I do that? Go in here? Yes, alright, okay. Ah. You can see I'm a veteran. um, yeah, that is streaming. Okay, cool. So, yes, that's right. Let me see if I can remember. So, let me look at the periodic table. Or is it a sexy one? There it is. Okay, so a period is, let me see if you can see this. Yeah, a period is this, I think, to the right, and then you've got the groups which are downwards. These are the atomic number, and the atomic number is how many. By the way, this might be wrong. I'm just revising. Atomic number is how many protons there are, and thus how many electrons there are, unless it's an ion. And then there's a positive or negative charge associated with the unequal distribution of those two components. Um, and then, okay, cool, that sounds about right. And then you've got, I wish I could point to this, I think I did this last time, but then you've got this 0.38, which is associated with I think it's like the atomic mass. Um, and the fact that it's point relates to the amount of ions, or the the kind of average over the ions that these elements have. I think that's right. I think that's right. That's right. Okay, so let me just go over that then. We've got this. So what is the center of an atom called? It is the nucleus. What is the charge on an electron? The electron is outside, so it's 1 negative, because I think the neutrons are the neutral charge. Which of the three subatomic particles is the lightest? It is the neutron. No. No, 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 no. Oh, gosh, I can't remember. I think this is wrong. I think this is wrong. The proton and the electron give it atomic number, but do not associate with the mass. We'll see what this is. This is definitely wrong. It's going to be the electron. Proton. Let's just look intuitively as well. Why would the protons be in the middle and the electrons on the outside? Gosh, you know what? I can't remember. Oh, this is really good. I'm glad we're doing this. Okay, I think this is wrong. If atoms contain charged particles, why do they not have a charge? If atoms contain charged particles, why don't they have a charge? They contain the same number of protons as electrons. What is the atomic number of an atom equal to? The number of protons in the nucleus. Number of protons and neutrons in the nucleus. Where are the electrons inside an atom? Protons and neutrons. Yeah, I don't think it is the neutrons. I don't think they have to be equal. No. They're the things that contribute to mass. So it's definitely not them. Yeah. Okay, that might be right actually. Where are the electrons inside an atom? The electrons are in no, they are arranged in any they are arranged in energy levels. The electrons are spread equally throughout the atom. Negative. Which elements have similar chemical properties? Elements in the same period of the periodic table. Elements with the same number of outer energy level. Elements with similar mass numbers. Well, the period is one to the right, so if I look back at this, these, if this is correct and that's the period, and I can't remember what I can't remember if it is or not, then the group is where the similar. No, hang on, because if you go down here, it gets more and more violent in terms of reaction. So it might be the period. Yeah, and it's yeah, I think it is that actually. Let's go for that. So it's elements in the same period of the periodic table, elements with the same number of electrons in the outer energy level. I mean, this must be right because that's where the I don't know. It's one of these. I'm kind of way to that, but I feel like this is the correct one for some reason. How many neutrons does this atom of carbon have? So it was something like if this is the you see I can't remember how this this is so good to go over again. If this was the protons, it's 6 it's 4 it must be 14 take away 6, which is 8, because 6 represents the electrons and the protons and the remainder is the mass from the neutrons. And they're roughly one unit of mass each. I don't know, that doesn't sound right. What are isotopes? Compounds with the same molecular formulae but different structural formulae. Atoms with the same mass number but different atomic number. Atoms with the same number of protons but a different number of neutrons. It's not that. Atoms with the same mass number but different atomic number. Oh god. I see. I thought it was when there was more electrons than protons. So what are isotopes? Oh, isotopes, not ions. Oh, I don't know. I have no idea. I can't remember. Hydrogen has 3 isotopes and a relative atomic mass of 1.0079. Which isotope is the most abundant? Um. Oh yeah. Wow. I don't know. So I've got some revision to do. Hydrogen has 3 isotopes and a relative atomic mass of 1.0079. Which isotope is the most abundant? Hydrogen with atomic mass of 1, 2 or 3. Why am I the most abundant will be the one with I don't know. I'm kind of guessing that one. So what did I get? Oh, I got 10 out of 10. Really? No way. 3 of those were guesses. Nucleus is the center of the atom and contains both protons and neutrons. What is the charge on electron? 1 negative. Next to the negatively charged subatomic particles. Which of the 3 subatomic particles is the lightest? The electron. Okay. It's so light compared to the proton and neutron that it has negligible mass. If atoms contain charged particles, why do they... I hate that word. Why do they not have a charge? They contain the same number of protons as electrons. Okay. Atoms are neutral because they have equal numbers of protons, positive charges, as electrons, negative charges. What is the atomic number of an atom equal to? The number of protons in the nucleus. The atomic number is equal to the number of protons in the nucleus of an atom. Cool. Where are the electrons inside an atom? They are arranged in energy levels. Inside an atom, the electrons orbit around the nucleus and are arranged into energy levels. Which elements have similar chemical properties? Elements with the same number of electrons in their outer energy level. Groups in the periodic table have the similar reactions or chemical properties, I see. The number of neutrons is calculated by subtracting the atomic number from the mass number. The number of neutrons is calculated by subtracting the atomic number from the mass number. Wow. I look crazy haired. Isotopes are atoms of the same element with the same atomic number but a different mass number. Isotopes are atoms of the same element. Isotopes are atoms of the same element with the same atomic number but a different mass number. Hydrogen has 3 isotopes and a relative atomic mass of 1.0079. Which isotope is the most abundant? Hydrogen with atomic mass of 1. The relative atomic mass takes into account the proportion of each element. So I don't understand this one again. Yeah, I can't remember this one at all. So I need to actually remember this. Yeah, let's go revise. Everything in the world is made of atoms, negatively charged, positively charged, particles with no charge, also contained in the nucleus of the atom. They also have a mass of 1. Atomic mass unit? I can't remember. AMU. Atomic mass unit, yeah. Electrons orbit a central nucleus of protons and neutrons. The nucleus has an overall positive charge as it contains the protons. Oh, that makes sense, okay. Every atom has no overall charge, neutral. While atoms do contain charged particles, they have the same number of positive protons as negative electrons. I also feel like the video is coming through really bad quality. I'll try and work on that next time. It should be better than that. Like, I'm pretty sure my connection can support it. Settings, video, bicubic sharpened scaling, 16 samples. Okay, I'll have a look at that for next time. Right, every atom has no overall charge. Okay, we know that now. The periodic table brings order to information. There are more than 100 elements which are arranged, represented by a symbol, blah blah blah. Chemical elements are arranged in order of increasing atomic number. The horizontal rows are called periods and the vertical columns are called groups. Okay, elements in the same group have similar chemical properties. This is because they have the number. Elements in the same group have similar chemical properties. This is because they have the same number of outer electrons and the same valency. Oh yeah, this word, valency. Measurement that shows the number of hydrogen atoms that can combine with one atom of a particular chemical element to make a compound. Valency, a measurement that shows the number of hydrogen atoms that can combine with one atom of a particular chemical element. Not this again. I need to go to sleep or something. Valency, a measurement that shows the number of hydrogen atoms that can combine with one atom of a particular chemical element to make a compound. Used to describe how easily an element can connect in a chemical way with others. Zinc has a valency of 2. Let's go and have a look at zinc. Where is zinc? Zn. Zinc. I wonder why that is. A valency of 2. Alright, well, fine. An example of a group in the periodic table is the alkali metal group. This video clip shows some of the reactions that occur with this group. Yeah, I remember that. Alright. Alkali metals. The elements in group 1 are known as alkali metals. They react rapidly, very fast, with water, producing an alkaline solution and hydrogen gas. The metals become more reactive as you go down the group. Halogens. The elements in group 7 are known as halogens. Fluorine and chlorine are gases. Bromine is one of only 2 liquid elements. Iodine is solid. They exist as diatomic molecules. Di meaning di. Because bi is 2. I think di is also 2 though. Diatomic. Just want to check etymology. It probably tells me. Oh, okay. Interesting. Let's diatonic. I meant to say diatomic. Etymology. 2 atoms, yeah, di, okay, fair enough. Right, they have 2 atoms in each molecule. As you go down the group, the halogens become less reactive. So this is fluorine and chlorine, group 7. 1, 2, 3, 4, 5, 6, 7, fluorine and chlorine. Bromine, and it says as you go down the group, become less reactive. That's interesting. Whereas these become more reactive, these become less reactive. Okay. Noble gases. The elements in group 0, they don't react at all. The transition metals are elements which are found between groups 2 and 3. Well-known examples are iron, copper, and gold. They're generally quite dense. Okay. The atomic number of an element tells you how many protons that element has. This is written at the bottom left hand side. Since elements are neutral, we know that the sodium atoms must also have 11 negative electrons to cancel the charge from 11 positive protons. The electron arrangement, yeah, that makes sense. The electron arrangement of all atoms can be found in the data booklet. All the electrons are arranged into energy levels. These energy levels can only hold a certain number of electrons. The first energy level can hold a maximum of 2 electrons, with the others being able to hold up to a maximum of 8, 288, yeah, I remember that. Sodium has 11 electrons. The first 2 fill the innermost energy level. The second energy level is also full, holding 8 electrons and 1 electron. Sodium, Na, where are you? Sodium, 22.990. The mass number is given at the top left of the element symbol. For example, sodium has a mass number of 23. We know that the atomic number of sodium is 11. This tells us that sodium has 11 protons, and because it is neutral, it has 11 electrons. The mass number of an element tells us the number of protons and neutrons in an atom, the 2 particles that have a measurable mass. Sodium has a mass number of 23 atomic mass units. Since sodium has 11 protons, the number of neutrons must be 23 minus 11, 12 neutrons. Here's examples. Yeah, we get that. Isotopes are atoms with the same atomic number but different mass number. So let me have a look through these. The masses. So this one, like, do they all have? Oh, here we go. Here's one. So francium is. I wonder what's so special about the square brackets. Okay, fair enough. Um, Elements are made up of isotopes, so the mass given in the data booklet is called the relative atomic mass. The relative atomic mass of each element shown in the data book is calculated from the masses of all the isotopes of an element, taking into account the percentage proportion of each. The relative atomic mass of each element shown in the data book is calculated from the masses of all the isotopes of an element, taking into account the percentage proportion of each. So where I'd like to see these, so if I go to this book, does it have these things? Relative atomic mass, density, date of discovery. Mm, not really. Um, I'd like to see all the different types. So isotopes of chlorine, for example. That's better. Oh, that's so cool. So let's ticket number 37. I meant to say take a look at, and then it came out as ticket number. Ticket number 37. Chlorine 37 is one of the stable isotopes of chlorine, the other being chlorine 35. Its nucleus contains 17 protons and 20 neutrons, for a total of 37 nucleons. Alright, cool. Um, since the relative atomic mass of chlorine is 35, chlorine 35 must be more abundant because its mass number is closer to the relative atomic mass. Okay, fair enough. That's good to know. Good stuff. Let's go back out of here. What else we got? Rates of reaction, bonding and properties of materials, chemical equations, the mole and concentration solutions, acid. Yeah, I need to know all this stuff. That's really important to know this stuff. I think I think after this I'm gonna try a tool. Um, pick two very simple molecules, elements, and then try to bind them together using some reaction, and see if I can work that out. I think that is probably a good path to figuring out quite a large selection of things. Because I'm thinking if I want to put down all the structures of nucleic acid onto sheet of paper so it's in my head, um, I'm going to need to know how to formulate those in the skeletal formula or whatever. Um, just having a think. Yeah, it's probably a good idea. So I'll finish this. I tell you what then, I'll finish this today. I'll do this today. And then I think next lesson I'll go over it again. And maybe one more time after that. So maybe next week, maybe Wednesday and Friday, maybe. Or maybe Tuesday and Thursday, depends on when I'm gonna go out and actually live a life. I'll try and do that with 2 revision cycles, and then I'll move on to drawing my first chemical formula, if that's possible at that time. Yeah, okay. Let me just make note of that actually. So we're on episode 7. Come up with a small plan. So we are going to revise. We're going to revise all these bad boys. We're going to revise what was learned. Come up with a small plan. That plan is for episode 8 and 9. Here. Oh, and I also just remembered. I don't know what's on my screen now. You see, lots of stuff. Let me just whack that. Whoa! Put all of this stuff into this one. Oh, you know what I just did? I'm an idiot. Sorry, people. I want all that to go into here. There it is. There we are. Right, we'll have to sort that out at some point. I just need to update this image. Just realised. Otherwise, well, I'll do it later. Whatever. It's not important. Let's do this. Rates of reaction. The speed of a chemical reaction is affected by a temperature, concentration, particle size. The speed of a chemical reaction is affected by temperature, concentration, particle size, and the presence of a catalyst. It can be calculated by measuring changes in reactants or products. Factors affecting reaction rate. For a reaction to occur, the particles that are reacting must collide with each other. Only some of all the collisions that take place cause a chemical change to happen. These are called successful collisions. The greater the number of successful collisions, the faster the rate of a reaction. This is called the collision theory. There are four factors that affect the rate, speed of a chemical reaction. Temperature, concentration, particle size, and use of a catalyst. Alright, sweet. Glad to know that button works. Temperature. If the temperature is increased, the particles have more energy and so move quickly. Increasing the temperature increases the rate of reaction because the particles collide more often and with more energy. The higher the temperature, the faster the rate of reaction will be. Sodium and chlorine react vigorously when heated, giving an orange flame and producing white sodium chloride. Sodium chloride. That's interesting, yeah. Sodium plus chlorine equals sodium chloride. That's so it's 2 sodiums as a solid plus chlorine. Can't remember what that means. Converts to 2 sodiums and a chlorine as a sodium chloride as a solid. Okay. Watch this video to correct procedure for this demonstration.
In this experiment, we are going to react metallic sodium with chlorine gas to produce sodium chloride. There are different ways to carry out this experiment. For this version, we will use a fume cupboard, a Bunsen burner, a heat-proof tile, a glass jar with lid, a scalpel, paper towel, sodium metal, and chlorine gas. Let's start the experiment. A small piece of sodium metal is cut using a scalpel, no more than a few millimeters on each side. This is possible because the alkali metals, including sodium, are soft metals. The rest of the sodium is returned to the jar, and the lid is put on. A paper towel is used to carefully remove excess oil. Chlorine is a toxic gas, so prepare and empty the gas jar in a fume cupboard. You can see the green colour of the chlorine in the gas jar. The sodium is placed on the heat-proof tile. Then play the flame of a Bunsen burner on it. It melts quite easily to form a hemisphere, but it does not catch fire easily. The yellow colour in the flame is produced by vaporised sodium. Before it cools, we take the lid off the gas jar and invert it over the hot sodium. Immediately, the sodium burns in the chlorine, and the gas jar fills with white particles.
So cool.
These particles are sodium chloride. Once cool, you can remove the jar. It is safest to do this in a fume cupboard, as there may be some chlorine left in the jar. You can see there is white powder on the inside of the jar and on the tile. This is sodium chloride crystals, the same salt used for flavouring food. By using a precipitation reaction, you can show the crystals contain chloride by dissolving some of the residue in distilled water and then adding silver nitrate solution. You get a white precipitate of silver chloride, the test for chloride ions. This shows there has been a chemical change and that a chloride has been produced.
Ah, go back. What was that? Sodium chlorine plus silver nitrate. Silver is Ag, is it? Ag. Ag, 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 ag. Ag, 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 ag. Where is it? Silver. I didn't know that. That is fascinating. And nitrate, that's nitrogen and oxygen. Oh. No, it's not. Nitrate. Where is NO? Hello. Nitrogen and oxygen. Must be. Yeah. Nitrate. Yeah, okay. So nitrogen oxygen bound equals, so the silver and the chlorine react and you get a gas, I guess. Nitrogen, no, Na is sodium. Oh yeah, sodium nitrate, right, okay, makes sense. Okay, cool. Nice.
Has been produced. Let's recap the experiment. A small piece of sodium is placed on a heat-proof tile. Then play the Bunsen burner flame on it. Take the lid off the gas jar and invert it over the hot sodium. The sodium burns in the chlorine, producing a yellow flame and white particles. These particles are sodium chloride. Once cooled, remove the jar in the fume cupboard. White sodium chloride powder is left behind. Key points. Chlorine is a toxic gas, so prepare and empty the gas jar in a fume cupboard. Sodium is highly reactive, so only a small piece should be used.
Sodium is highly reactive, so it's going to be down the bottom somewhere. No, not necessarily. Sodium is highly reactive, so it's going to have a lot of electrons on the outer. It's going to have more electrons on the outer shell of energy, and that means that I wonder what it is, what its structure actually is. Can I click on this? Yeah, I can. Electron configuration. 3s1. I wonder what that means. Damn it. Let me just look that up. Understanding electron configuration. While these electrons all stick within the atom, because of their attraction to the protons, they also mutually repel each other, causing them to spread out around the nucleus in regular patterns. Oh, bless, Khan Academy is great, but very slow. How do you read electron configuration? Oh, this is awesome. Okay, let's just watch this.
The first thing we need to do to find electron configurations is to find the number of electrons for the element. So we can find this on the periodic table, and we're going to look at the number above the element symbol, which is called the atomic number. That'll tell us the number of protons, but it also tells us the number of electrons. And we can use that number as we try to find the electron configuration for whatever element we're interested in. So we'll try an example with boron. You can see we have this chart here, and this is the general format you'll see them in. We have boron. We know we have 5 electrons. So we'll follow the chart, and we'll go down the 1s. So we write 1s, and we know that 1s holds up to 2 valence electrons. So let's put 2 electrons there. Then we have the 2s, following the arrow down there. That holds 2 electrons as well, since it's an s orbital. And we've used 4 electrons. Remember, we have 5 for boron. And we go down this row here with the 2p and the 3s. Well, we only need 1 more electron to get 5. We know that the p holds up to 6, but we only need 1. So that's our electron configuration for boron. 1s2, 2s2, 2p1. Notice that the numbers add up to 5, just like the number of electrons for the element. Let's try another one, chlorine. So for chlorine, we have an atomic number of 17 protons, but importantly for us, 17 electrons. So we'll go down, we have the 1s, and that holds 2. We then have the 2s, that holds 2, since it's an s orbital. And then we'll go down 2p, which holds up to 6, and we'll put 6 in there. And if you add those numbers up, we've used 10 electrons so far. We have 17. And after the 2p in that row, we have 3s, which holds 2. We've used 12 electrons now. And then we'll go down this row here where we have the 3p, and p holds up to 6, but since we have 12, we only need 5 more to get 17. That's the electron configuration for chlorine. Let's do one more. Vanadium has 23 electrons.
What do they say about the s orbital?
That holds 2, since it's an s.
What's an s orbital? An s orbital is spherically symmetric around the nucleus of the atom, like a hollow ball made of rather fluffy material with the nucleus at its center. As the energy levels increase, the electrons are located further from the nucleus, so the orbitals get bigger. Oh man, this is amazing. Okay. Right. Where were you? Look at the graph of the reaction between hydrochloric acid and calcium carbonate. Notice how an increase in temperature leads to an increase in the speed of release of carbon dioxide, but not the total volume of carbon dioxide released. Volume of gas produced, time from start of reaction. Volume of gas produced goes up, and the time from the start of reaction. Low temperature, high temperature. Look at the graph of the reaction between hydrochloric acid and calcium carbonate. Notice how an increase in temperature leads to an increase in the speed of release of carbon dioxide, but not the total volume of carbon dioxide released. I see, okay. Yeah, I see. Okay, cool. That's awesome. If the concentration of reactants is increased, there are more reactant particles moving together. There will be more collisions, and so the reaction rate is increased. The higher the concentration of reactants, the faster the rate of reaction will be. Makes sense? By decreasing the particle size of a reactant, we are increasing its surface area. The greater the surface area, the higher the chance of collisions, thus the faster the rate of reaction. The smaller the particle size, the faster the reaction. Think of a cube where the length of every side is 2 centimeters. The area of one face of the cube will be 2 by 2, which is 4 centimeters squared. Cubed. Squared. 4 centimeters squared. The cube has 6 faces, so the total surface area is 4 centimeters squared times 6 equals 24. We could cut that cube horizontally and vertically along each face so that we have 8 smaller cubes. Each of the small cubes has a face area of... Yeah, okay, I understand this. Videos, demonstrations with charcoal, gunpowder and steel wool that show the effect of particle size and concentration on reaction rate.
Increasing the rate of reaction.
Start them off, and when we get to the end of the race, the solution's going to turn blue. Are you ready?
Yeah.
Steady, go. And now let's just mix them up.
The reaction taking place in the beaker finishes with the sudden release of iodine, which interacts with the starch that is already present to turn the solution blue almost instantly.
Almost instantly. Use of a catalyst. A catalyst speeds up the rate. Elephant's toothpaste experiment. The elephant's toothpaste experiment shows how a catalyst can speed up the rate of reaction. Hydrogen peroxide breaks down slowly into water and oxygen. Hydrogen peroxide breaks down slowly into water and oxygen. Adding a catalyst such as sodium iodide or potassium iodide. Let me just... Etymology of iodide. Salt of hydriodic acid. Binary compound of iodine and another element of radical. Or radical, okay. Makes it sound much more quickly as shown in the video below. Elephant's toothpaste.
In the elephant's toothpaste experiment, we are going to be looking at the effect of a catalyst on breaking down hydrogen peroxide. The same process can be shown by this smaller experiment. Hydrogen peroxide is corrosive, so gloves and goggles must be worn for this experiment. Hydrogen peroxide solution is poured into a small measuring cylinder. The hydrogen peroxide is very slow breaking down. A glass rod coated with manganese dioxide is dipped into the cylinder. Bubbles immediately start to form as oxygen is given off. The manganese dioxide acts as a catalyst, turning the hydrogen peroxide into oxygen and water. There are many other catalysts.
Hydrogen peroxide. Hydrogen peroxide. So there's two because I wonder if that's what that means. I wonder if that's what that means. Usually hydrogen dioxide is called hydrogen peroxide because it contains more oxygen than hydrogen can attach directly, and there is oxygen-oxygen chemical bond in this compound. All compounds containing group are called peroxides. Hydrogen dioxide is called hydrogen peroxide because it contains more oxygen than hydrogen. Okay? So, more hydrogen, no, what's this? God. More oxygen than hydrogen. More oxygen than hydrogen. And then that goes to plus an oxygen. I don't
for this
understand it.
reaction, including several transition metals. The enzyme catalase found in potatoes and liver will also break down hydrogen peroxide. The elephant's toothpaste experiment uses sodium iodide solution as the catalyst. For this experiment, the following equipment is needed: a large measuring cylinder, sodium iodide solution, 60 cubic centimetres of hydrogen peroxide, washing up liquid so that the bubbles produced make foam, food colouring to make the bubbles more visible, a splint, and a flame source. Let's start the experiment. 60 cubic centimetres of 100 volume hydrogen peroxide is added to the large measuring cylinder. Then a small amount of food colouring and washing up liquid is added. Then 5 cubic centimetres of saturated sodium iodide solution is added. You can see a large quantity of foam is produced very quickly. You can also see that the bubbles are steaming. This reaction is very exothermic, so the mixture becomes hot. This increases the rate of reaction further.
Enzymes are biological catalysts. They occur naturally in the body and help with digestion. They are used in the production of alcohol zymase, and digestion of food, amylase. I remember all these words from GCSE. Enzymes are specific. This means that they can only catalyze one reaction. Enzymes are specific. Okay, that's interesting. Increasing enzyme activity. Oh yeah, 40 degrees. Oh, 37, the optimum temperature. Okay, cool. The rate of a chemical reaction is a measure of how fast the reactants are being used up and how fast the products are being made. The rate can be determined by measuring changes in the concentration of the reactants or products, changes in the mass of the reactants or products, or changes in the volume of the reactants. For example, when dilute hydrochloric acid reacts with zinc metal, zinc chloride and hydrogen gas are produced. There are two simple ways to measure the rate of this reaction in the lab. If the reaction is set up on a balance as shown, set up on a balance? Do you mean a scale? Set up on a scale as shown, the mass of the apparatus can be monitored throughout the reaction. As hydrogen bubbles escape, the apparatus will lose mass. Yes. Zinc plus hydrogen chloride. Changing mass during experiment. An alternative way to monitor the reaction is by collecting and measuring the volume of the gas as it is produced. The gas can be collected in a gas syringe or over water, as long as this is insoluble in water. Volume of gas collected, gas syringe, conical flask, zinc plus hydrogen chloride, trough of water, volume gas collected. Yeah, that makes sense. Measure, yeah, cool, got it. Calculating the rate of reaction. Using the results of experiments like these, the average rate of the reaction can be calculated. No matter which quantity is measured during the course of a reaction, the average rate of reaction can be calculated using the equation below. Oh, gosh. Average rate equals change in measurable quantity divided by the change in time. Yeah, I really should call this different. This was 7, yeah? Episode 7. Yes, indeed. Learning about basics of chemistry. Let's do that now whilst I'm here, not that. Seven. Desktop. Yep. Yep. Save. So the change in measurable quantity divided by the change in time. Change in measurable quantity divided by the change in time gives you the average rate of reaction. Average rate of reaction is the change in measurable quantity divided by the change in time. Wow, I wonder who worked that one out. This equation is sometimes written as rate equals change in quantity over change in time. Change in measurable quantity can be read from a table of results or from a graph produced from results. As the rate is changing throughout the reaction, we are calculating the average rate over a given time period. For example, the graph below could be used to calculate the average rate over any period of time. Mass produced, the time, change in mass, change in time. Okay, yeah, I see calculus. Cool. dx over dy. dy over dx, yep, cool. Using this graph we can calculate the average rate between 30 seconds and 120 seconds. Average rate equals change in mass, change in time, so this is the derivative, is the rate. Yeah, the unit that average rate, yeah. The unit that the rate is measured in depends on the measurable quantity. Since a change in mass is measured in grams and a change in time in seconds in the example, the unit of rate would be grams per second. Similarly, if a change in concentration is measured in moles, then rate will have the unit moles per litre per second, or a change in, yeah. In chemistry, graphs can be used to follow the course of a reaction. A graph can tell us many things about a reaction. Higher temperature, higher concentration, small pieces, lower temperature, lower concentration, larger pieces. The magenta line is a steeper gradient and represents conditions favouring a faster reaction than the red line. When the reaction is finished, the end point represented by the dotted line, the graph goes flat as no more products are being produced. Yeah.
Happen at different rates. They occur when particles collide. The more frequent and energetic the collisions, the faster the reaction is. There are slow reactions, like a car rusting, and there are fast reactions, such as explosions. There are 4 factors that affect the rate of a chemical reaction: temperature, concentration of solutions, the surface area of reacting solids, and the presence of a catalyst. There are 2 ways to measure the rate of a reaction: by the rate at which a reactant is used up, or by the rate at which a product is formed. And there's a word equation for this. In any chemical reaction, reactants produce products. You can choose to measure either, but the measurement will depend on the nature of the reactant or product. Let's look at the rate of reaction between calcium carbonate and hydrochloric acid. These 2 chemicals react to form calcium chloride, carbon dioxide, and water. There are several things that could affect the speed of the reaction: the hydrochloric acid's concentration and temperature, and the calcium carbonate surface area. The overall reaction can be affected if you stir it or use a catalyst. To plot a graph measuring rates of reaction, you would record the mass or volume at regular intervals and plot this on the vertical axis against time on the horizontal axis. The steeper the curve, the greater the rate of reaction. The rate will normally be greatest at the start due to the higher concentration of reactants, and when the line levels out, the reaction is finished. Using smaller pieces of calcium carbonate with a greater surface area, increasing the concentration of acid and increasing the temperature will all increase the rate of the reaction because the particles are colliding more often and with more energy. This graph shows the volume of carbon dioxide produced over time. The lines show how changing concentrations make a difference to the rate of the reaction and volume of carbon dioxide produced. All reactions produce the same volume of carbon dioxide, but the higher the concentration of hydrochloric acid, the greater the speed of the reaction.
Cool. Which of the following factors will not speed up a chemical reaction? Increasing the temperature, increasing the particle size, increasing the concentration. Increasing the particle size. A pupil places 10 grams of potato into 1 mole of hydrogen peroxide solution. The potato has a biological catalyst inside it that breaks the hydrogen peroxide down to water and oxygen gas. What term is used to describe a biological catalyst such as catalase? Enzyme. A pupil places 10 grams of potato into 1 mole hydrogen peroxide solution. The potato has a biological catalyst inside it that breaks the hydrogen peroxide down to water and oxygen gas. The pupil counts 15 bubbles of oxygen given off every minute. What could she do to the 10 grams of potato that would increase the number of bubbles per minute? Cut it into smaller pieces. A pupil places 10 grams of potato into 1 mole of hydrogen peroxide solution. The potato has what would happen to the number of bubbles per minute if she used a less concentrated hydrogen peroxide solution instead of the original? It would decrease. What would happen to the number of bubbles if the temperature was increased to 30 degrees? Increase. Which of the following reaction would be the fastest? 1 mole of hydrochloric acid reacting with zinc powder, 1 mole acid reacting with a lump of zinc, or acid reaction with zinc powder because it's small. In which of the following reactions would hydrogen be produced the fastest? Calcium powder and 2 moles of acid, calcium lumps, calcium powder and 4 moles of acid. What does a catalyst do? It speeds up reaction and is not used up in the reaction. Speeds up reaction and is used up in the reaction. A pupil monitors the rate of a reaction by measuring the volume of gas that is being produced every 15 seconds. What will her units be when calculating? Pupil monitors the rate of reaction by measuring the volume of gas that is produced every 15 seconds. What will her units be when calculating the rate of reaction? I don't know what a mole measures. A volume. Of volume of gas that is produced every second. Which line of this graph shows the slowest reaction? The slowest reaction is C. I think I got one wrong. Yeah, oh, 2. Okay, yeah. What was it? What was the ones I got wrong? Yeah. What does a catalyst do? Speeds up reaction is used up. Okay, and are not used up in the and can be reused. Okay, cool. A pupil monitors the rate of reaction by measuring the volume of gas that is being produced every 15 seconds. What will units be? When a change in volume is measured in centimeters cubed and time in seconds, the correct unit of rate. Okay, cool. I didn't know that. Nice. So yeah, we'll do this. Come up with a small plan. That is plan. Came up. That plan is for 8 and 9. We are going to revise what we learnt here. We are then going to start concentrating back on formulas. I need to start getting a bit mathy about it because when I am trying to do these CRISPR reactions, I need to understand what I'm doing, and I'm not going to be able to do so many experiments, or any experiments maybe, so I need to understand them theoretically, and then come up with the goods first, basically. So, but this is good. This is a nice little way, and it's nicely structured as well. So what I'm going to do is I'm going to one of two things: either take a break and go for lunch and come back and do it, or I'm going to pick this up on Tuesday. I'm not sure how I'm feeling. A bit tired because I woke up early, but that is the goal. So, and that's what I'm going to do in episode 8. So thanks for watching, and see you on the other side.